Welcome to another video for Stat 420. In this video, we're going to very briefly talk about the F-test and how it relates to judging model significance in regression. So we'll talk a little bit more about this when we get to multiple regression. We'll also talk about Anova in general. But it does kind of help to relate it because it will come out in our summary output in R when we're looking at the summary of a model. And so let's just kind of talk about, how it connects to this and what an F-test is even representing. So first off, an F-test is typically used to compare the variance of two different samples. So if we have, say, sample A and we have sample B, and we notice that the variances are different, maybe we want to test to see, do we have evidence that these two samples must come from different distributions with different variances, or is it still plausible that they could just be two samples from the same distribution with the same variance, or at least they're two samples from distributions with the same variance, even if the distributions might be different. So the F-test can help us decide if that difference could be explained by random chance or not. So the reason that we might see an F-test in regression is because we might be comparing the variability in our linear model with the variability of not having the variability of, say, a null model, the variability of a model that does not depend on X. So when we compare those two variance amounts, we can run an F-test to see if we have evidence for a significant change, or if that difference in variability could really be explained by kind of random chance sampling. And one thing to note here is that when we're working with simple linear regression, an F-test is kind of redundant and doesn't really add anything that we're not already getting from the t-test for the slope. So the t-test for the slope and the F-test for regression will actually produce the exact same p-value. So again, it's not adding anything in a simple linear regression situation beyond the t-test. When we get to multiple regression and comparing maybe different models, then that might be a little bit more helpful. So the construction of an F statistic is just going to be the variance of one distribution of one sample divided by the variance of the other sample. And if you think about how kind of our decomposition of variance in a simple linear model, what we have is our total variation represented over here. So this is if we don't fit any kind of model right here. And so it's just going to be, my pen is being a little bit weird. I think it's because it got a little bit unscrewed there. There we go. Okay. So this is the variation in y as compared to y bar. So this is the total variation in the y variable to begin with. And we can, when we run a linear model, we can break that variance up into two subparts. One is the variability of y from our regression line. So this is the sum of squares error. It's the variability that our regression equation is not explaining. And then this piece of variance is the variation from y hat to y bar. So this is the amount of variability that our regression model is explaining, right? So we have variability explained, variability unexplained adds up to the total variability that we started with. So what we can do is we can compare the, let's see, this is going to be the variability explained divided by the variability unexplained to see if there's going to be a difference in those two variances. And so the F-test, basically if the null hypothesis is true and these variances are coming from distributions with the same variance, then I'm going to see a ratio generally around 1. But obviously because of random chance, it might be a little bit lower, it might be a little bit higher. But if my F statistic is like unusually high, right? So like if I'm getting to an F ratio that's like, around above 2 and heading to about 3, 4, 5, that's getting to be pretty unusual. That means that my variance for one sample is about 3, 4, or 5 times higher than the variance for the other sample. And that's when I start to say, hey, this is evidence that there might be a difference in variability, that the variability I'm explaining with my model is unusually high compared to the variability that I started with. So when we judge the test result, we're just judging the null hypothesis again that the slope is 0, that there is no relationship, that there is no model depending on X. The alternative would be that the model does depend on X and is finding value in doing that. So we don't really we don't care about calculating this by hand, honestly. We just care about seeing it in our regression result and noting that we get an F statistic, it produces a p-value, and in a simple linear model, that p-value will match the p-value for our t-test for slope.